Welcome back to Pardeslines. So today I want to go with you on a great project. We are going to see together how to estimate a transformation matrix applied on a 3D object, a 3D point cloud. So let's imagine we're going to start with our Stanford Bunny mesh, then to convert it in point cloud. After that, when we convert it in point cloud, we want to apply on a copy on this point cloud, want to apply a transformation matrix. What is a transformation matrix? So let's see that. A transformation matrix is containing first a rotation matrix. It's an array of 3 by 3 components, okay? And how to build it? We need to build it using an array of Rx. And you see here in this array, we have the cosinus and the minus sinus, and the sinus and the cosinus of a degree in radian. Okay, we just need to precise that. And then this rotation will be applied around the x-axis. The same thing for the y-axis and for the z-axis. You can see here that the cosinus and the sinus are in different places. And then we just need to apply dot product in order to combine them together and to get the final rotation matrix we want to apply. Okay, so let's go ahead. Okay, we can see here our rotation matrix. It's a 3 by 3 array, and we can see here the values. Then we also need a translation vector. And here we have the values of the translation vector. Then we need to combine them in a 4 by 4, because also Open3D is working with 4 by 4 transformation matrix. And so it's always useful to have it together. So let's build it, np.i of 4 to have an array of only 0, and then to have like a placeholder array, and then to integrate the ground truth of rotation and the translation vector. You can see here the matrix. Yeah, this is ground truth T containing 4 by 4 component, and we can find here our rotation, here our translation, and here 0, 0, 0, 1. Okay, so then we want to use an algorithm. Okay, let's pre-process it and receive the fast points, the FPFH, which is a fast point feature histogram. So what is exactly? I'm going to explain that. It's like a descriptor. So let me just go ahead until the next breakpoint. Okay, so this is after we applied the rotation and the translation on the original point cloud after the sampling from the mesh. Then, so after that, I just computed here. I just need to compute here the source FPFH using the pre-processed point cloud with a function of Open3D, sorry, to compute the features, the FPH features, and you can see here compute FPH features. So what does it mean exactly? It's like a descriptor of the 3D point cloud. So let's imagine just to extract from the 3D point cloud to extract the features. Why we need that? Because the RANSAC algorithm will use those features to find the corresponding pairs of points. So the goal of the RANSAC algorithm is first to find the pairs of points between the source point cloud and the target point cloud, when the source point cloud is our original point cloud and the target one is after applying the transformation. So then the RANSAC algorithm will find the correspondence between points and try different transformation by iteration. And when applying a first transformation on a pair of point cloud, on a part of the point cloud in the corresponding pairs, then the RANSAC algorithm will try the same transformation on other pairs. And when the RANSAC algorithm finds the corresponding pair as and applies a lot of times the same transformation and find the in layers, so the RANSAC algorithm can output the transformation estimated. Okay, it's like, as I said at the beginning, it's like a pre-processing of the ICP. So let's apply it and see the results. So this is after just a downsampling again, and then we apply the RANSAC algorithm, and you can see here that our 2 point clouds are completely aligned. What does it mean? Meaning that now we already find the RANSAC result transformation, and we can see that here. Let's take it, and we can see this is the transformation. And we can already see that is completely aligned with our first rotation and translation vectors that we initialized at the beginning. Then we need to just refining using the ICP iterative closest point. The iterative closest point algorithm is using a loss function, sum for loss, which is minimizing the original point cloud, the points inside the original point cloud, minus the target after applying the transformation estimated by the ICP. By minimizing that, we want to get 0 between the corresponding points between the original point cloud and minus the final after applying the transformation estimated by the ICP. The only thing that is that we used RANSAC is also to initialize the ICP. As you can see, execute ICP algorithm, I take in input the RANSAC result transformation. So let's go ahead, and now we see this is the result after the ICP, is that we have only one color. Why? Because it's exactly the same points. Because the local refinement is very great. We have now a 2-point cloud on the same place exactly, and so you can imagine that we get the exact same transformation. Why it's so exact and why it's not like with a small error? Because it was exactly the same point cloud. Okay, I haven't did like a different sampling or something like that. I just took the first original bunny mesh, then downsampling, and then apply on the same mesh a rotation and a transformation. So because I did that, so I cannot have any error when I used RANSAC and then ICP. But if it was like a different sampling, or it was, for example, a different point cloud, a little bit even, then it's completely feasible and possible to get some error. And now we can also see the ICP result transformation. And we see now that it's exactly the same than the original transformation we applied. And also I printed here some metrics, so we can see the fitness, the root mean square error, the rotation error, and we can see that all the results are perfect. So what you can do on your side is to change the sampling of the original point cloud. And instead of applying a rotation on the exactly same point cloud, you can apply a rotation and a translation on a different one, meaning the same original mesh, but applying just a different sampling. And then you will see that maybe you will get different error. Why? Because the corresponding points will be more challenging to get them. And for that, the RANSAC algorithm will maybe will be more difficult for him, and then same thing for the ICP. So that's it for this video. I hope it was great for you. Please subscribe to the channel. Thank you. Bye.